Okay, welcome to Intro to Probability. This is a fun class. I love probability with all of my being, right? So, and there's a lot of interesting stuff that you will learn. You will also use quite a lot of the math that you have learned here, and you'll see how it applies in probability, right? So the way I teach is I give notes that are not fully filled in. You will realize. Right? I asked you to prepare the chapter 1 and 2. I hope you have that. You can do it on your machine and all that. That's fine. It's up to you. Um, and so I do discuss examples as well because a lot of probability is learned by basically going through problems, and that's what I hope to do with you all. So the I also realized that some of you you want to listen to me, so it can be hard to listen and write at the same time. So of course I give you time to write, of course. But if at any time you feel that you cannot keep up with writing everything that I have on the screen, please feel free to take a picture. That's it. You don't ask permission. I'm not weird like that. Right? You can take a picture at any time. Now, not many students, but some students in the past have said, can you supply us with all your slides? Now, I don't do that, and I'll tell you why. Because math is not learned by reading complete slides. Trust me. Right? Maybe you are in the 1% of people that can learn math by reading things, right? But I'm not like that. Most people aren't like that. You actually learn by writing. Trust me. It's true. So here's what I advise you. If you take a picture at the end of the day, or at least end of the week, go back and look at the gaps in your notes and fill it in this week, right? That week you will learn because you'll revisit it. It's much better than me giving you full slides. But if you get full slides, who's going to copy it anyway? Because you know, right? So you learn by doing. Now, the other aspect of this class is we have quite a lot of group work. So this place is naturally set up for that. So this is kind of the group that you'll be working with. Now, if you don't like people that you're at your table, I don't think is a thing. So this today's group work's not going to count, in other words, but you can next time sit with people that you want. But I don't think that's going to happen. All right. So this will be kind of the group. So don't change around because it makes administration of the group a little bit more complicated. So I also do something a little bit different because this is a math class. I don't just give you problems to do as a group. Many times I ask you to write me a problem as if you're writing it for an exam. And I found that to be very effective in helping students do it. So it's like you be the professor and write me a question like what I've done, and then you provide a solution. Like something like that. So you will see an example of this today, actually. Start. All right. So any questions before we do? Okay, good. So let's start. So probability uses a lot of set theory, and so we will review some of that. Some of this may not be new to you, and some is pretty easy actually. So what is a set? A set is a collection of objects. It doesn't have to be numbers, you know, a collection of objects. And the objects in the set are called elements. So if X is an element of set A, we write X is an element of A, right? That's the symbol we use. And if it's not, then we say something like this. Okay. So a set with no elements is called the empty set. Now, some people argue, hey, didn't you just say that a set contains elements? And now how can an empty set even be a set? You know, okay, I'm not going there, correct? Right? These kind of philosophical arguments, you can go check it out, knock yourself out online, right? There are people who argue that empty set is not a set because the set some things. So I'm not going to go there, but the empty set is a set with nothing. Not a set with zero, it's a set with nothing in it. All right. And it's symbolized by phi or that one. All right. I tend to use phi more. So the elements of a set must be unique. Now, what do I mean by this? So let's look at an example. So have your examples with you. Clearly, there are no solutions to the example. This is the writing part I'm talking about, right? So determine whether each of these sets are equal. So when I say a set must have unique elements. I cannot actually have a set that looks like 1, 3, 5, 1. So the this part has some problems for some people because they have a very, how do I say this? They have a very thing-oriented understanding of a set. They really think of it as a physical, like a Tupperware with boxes of things inside that you can take out and look at. It is like that, kind of, but it's more than that. So a set basically just tells you who belongs, and it's like there's an unlimited number of ones inside. It's not like, oh, I've taken one out and it's gone now. That's not correct. That's not the right understanding. So that's why it doesn't make sense to repeat. Oh, there's two ones in this set. That doesn't make sense. So a set doesn't behave that way. All right, you don't run out of ones because I've taken the one from there. It's gone now. I can't choose it again and things like that. All right. Now, a set where you can have repeats. It's called a multi-set. That's pretty high level. We don't use that at all. I mean, I'm sure there are some high level math applications that use that. Okay, we don't need that. Our set is a conventional set where every element is unique. That's important at the outset. So are these equal? Now, again, technically, how do you show that two sets are equal? Okay, so this class is a mixture of rigor and also common sense, right? The correct way to show that two sets are equal actually, does anyone know this? I'll give you the chance. Does anyone know how you show two sets are equal? Have you heard about this in another class? Share. Anyone know the, yes. Yes, okay, so only math students will appreciate answers like that. Yeah. So I've just come from an intro set class, which is like the other end of the spectrum. Right? I think you have done tutoring, you know what I thought. So what she said is exactly right. You will actually show that two sets are equal if one is a subset of the other and vice versa. And we will use that argument sometimes. But this one, I'm just going to use a common sense. You can do that. You get everything found here is found here and vice versa. So that's actually, and that's basically what I'm trying to say, right? Everything found in one set is found in the other. That makes them equal. And clearly B is not, right? The two sets are not the same because this one has a set that contains one. This has something else. So clearly these two sets are not equal. Okay. In fact, it's not too early to say this. A set that has sets in it is called a collection. Technically, it's a set, right? A set is a collection of anything, but we tend to call sets that have sets as their things a collection. But a collection is a set. All right. So the word collection is used to reflect a set whose elements are set. Okay. Okay. So these two are not same because you can find an element in one of the sets that doesn't belong in the other one. You can give a counter example. You can say, oh, look, this one has this thing, it's not found. Okay, so it's kind of basic so far. And I think this being a math class, most of you are quite comfortable with this. Of course, these are not the same entities, right? This is the set containing one. This is the number one. They are not at all. Different animal, right? So they're not the same thing. Okay, so we will go on. And okay, so I do sometimes indicate which examples we look at as we go along. Two sets are equal if and only if they contain the same elements. And when two sets are equal, we can say A is equal to B. So more along the lines of equality of sets means that everything found in one can be found in another. Now, there's another example here. Let's see, example 2. So let's say, and I picked this example for a reason. Not every set must always display its elements formally. I can define the elements of a set using words or mathematical symbols. We will be very comfortable with this as we go along. So let's say the set A contains all letters that belong to the word contrast. So list the elements of A. So again, this was picked with a reason. The word contrast clearly has two keys when you spell it out, but when we list down the elements of the set that contains the letters of contrast, do we repeat the key? The answer is no, we don't. All right. And I'll just, I mean, I'm not defined NA yet, but I'll tell you now. NA means how many members does a set have? What's the size of the set? So the answer to this would be just the set CONTRAS, all distinct. You don't repeat the E, and so the size of the set is 7. Right? NA just means size of set A, right? How many elements it has. Okay. Let's move on. Okay, if a set has a finite number of elements, we call this a finite set. Then NA is number of elements. So let's look at another example. All right. So the fact that there are finite sets means they're clearly infinite sets. All right. Finite number of elements, then we call it a finite set. Let's look at another example. So what is the size of each of these sets? What is N phi? Anyone? How many elements does phi have? 0. N phi is 0. Good. Right? So phi is clearly a finite set. But what about this set? What is the size of this set? Okay, technically I should call this a collection, right? Because it is a set that has a set inside. What is the size of this set? 1. It has 1 element. Right? Never mind that the empty set has nothing, but now this collection has sets as its elements. So the size of this set is 1. Okay, what about this weird set? Right? A, and then the set of A, then the set of A, and okay, so what's the size of this set? Right? How many elements does it have? 3. Good, right? Good. So I've twisted things around just to make sure you understand the element. Then there are three elements in this collection, if you like. Okay, good. Okay, now we say that a set A is a subset of B if and only if every element of A is in B. And now, of course, we are not saying equality here. So if you can show that everything in A is in B, that makes A a subset of B. That's all you need to show. So we write it like that. Now, I think some of you may wonder, you may have seen this symbol like that without the line. And some people distinguish between the two and say this is what we call a proper subset, which means that there are things. Okay, so some books, when they write this, they mean so that there's no consensus on this, and it drives me nuts actually. Some people write this symbol like this without the line, but they mean this. Okay, so I try to be a bit more careful. I always write this because this means the possibility that really B could have things that A doesn't have, or it could be that they are actually the same set. So it doesn't matter. It's kind of the analog is saying less than or equal. If I say X is less than or equal to Y, it doesn't throw away the possibility that X and Y are the same. Okay? That's exactly the analog in sets here. So don't be surprised. Don't come screaming at me. I saw this book that writes it like that, but yet the two sets are potentially the same. Some people are careless that way. They mean this, but they write it like that. So basically, it could potentially be the same thing. If you mean that they cannot be the same set, then some people go all the way and put a not equal to sign at the bottom or something like that. Okay. So just okay, let's look at some examples. Which ones are okay? Suppose A is 2, 4, 6, or the set of 2, 4, 6, B is okay. Determine which of these, this is really, really basic. So which one's a subset of who is not a subset of who, and all that. So clearly, I think B is a subset of A. Okay. C is a subset of A, but B and C do not have a subset kind of relationship because clearly they're things. Okay, this is very, very right. This is not hard at all. Okay. That's kind of all you can say. But this leads me to introduce a pretty easy visualization of sets that people like, and that's called a Venn diagram. They're pretty famous, right? Um, One thing I found quite interesting is somehow Venn diagrams are very established in American culture. You can almost say it in almost any audience, and people do know what they mean. This is not the case everywhere else. America is exceptional in this sense. I've seen people use Venn diagram in ordinary speech. It's not something you can do in outside America. Or people who wonder what planet you're from. They don't even know what you're saying. But America does seem to know Venn diagrams. And so it's just circles to represent the relative. Okay, so represent A is a subset of B, is a subset of C, using a Venn diagram. So something like this, right? One set is completely a subset of the other, so it's contained in a larger set, which is then contained in an even larger. But of course, all this does not remove the possibility that B and C could be identical sets. Okay, there could be nothing here. That's what I'm trying to say. It's just a picture, a convenient representation. Now you cannot use Venn diagrams to prove stuff, but they are very useful to visualize things. I would say. You can't use it as a proof. You can't say, "Oh, look, my picture says this." It's not a rigorous mathematical proof, but you can use it to help you understand relationships between sets. Right? They are pretty useful in that sense. Okay, let's go on. Is this true or not? Is X an element of this set? Yes, this is true, right? X is in this set, so yes. Is a set always a subset of itself? The answer is yes. You follow the definition. A subset is when everything in this set is found here. That's all you need to show. And clearly, this element is found here. So this is a subset of it. So that's true as well. But is this true? Right? Yeah, good. It's not true. Why? This is true. This is an element of this set, but this set doesn't contain sets. It contains X. So this is not an element of this. So that's false. Right? Okay. What about this one? Is this true? Is this set containing X an element of the collection of sets that contain it? Yes, that's true. Right? So I know these seem pretty trivial, but it's important. These things are important for you to understand. Now, if you are into programming, as I don't know, some of you may be from CN, I'm not throwing shade on coding or anything, but sometimes code is a little bit sloppy when it comes to things that R is, I can tell you, right? That a vector can be morphed into a scalar, and you do operations, arithmetic operations on vectors that don't make sense, and mathematically speaking. This is not good. This is very, 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 very precise. All right. So be careful. Okay. Is the empty set a subset of this set? Actually, the answer is yes. The empty set is a subset of every set. This is actually not trivial to prove because you can't even say this one. You probably have to say, actually, this has piqued my interest. How do you prove this actually? Or is it an axiom? I'll need to check this out. Right? Because you can't start with, oh, let's say X is in here, but X is not in here. Nothing is in here. So how do you go about proving this? Is actually a very interesting philosophical question, which you can go check it out. But I don't even know whether it's a definition. It might be a definition. You can't prove it. The empty set is a subset of everything. All right, it tags along. Right? Okay, but of course, is the empty set an element of this set? The answer should be no, it's not. Right? The empty set is a subset of every set, but it is not in this set because this set doesn't contain the empty set. It contains X. Okay, so that's false. Are we still on the same page together? Right? Okay, not too bad. Okay, now let's look at our, I guess, the first kind of probability like example. Consider the experiment of tossing a coin 3 times. All right. So E is the collection of outcomes with at least one head. C at least one head, and F is the collection of outcomes of more than one head. So compare two sets E and F. So even without listing out the elements at all, can you tell that one set is bigger than the other? Right? Clearly. Right? The set that has a broader criteria is going to be larger, right? So at least one means one or more. More than one clearly means two or more. Okay, so compare the two sets E and F. Clearly, if you want, you can list down all the things that could happen. And now it's not too early for me to say the universe of all outcomes that can happen when you do an experiment in from a probabilistic point of view is symbolized by S, sample space. And you know that when you toss a coin 3 times, these are the things that could happen. Okay? And so E and F are both subsets of S, clearly. And E has more elements than F does. By definition, by how F is defined. So a few technical terms that again I will start to introduce. The collections of outcomes, they are subsets of S and they are known as events. Right? So subsets of any sample space are events. I mean, these are terms that were coined because of how probability. Let's put it this way: probability is an old thing, but rigorous probability is new. Rigorous probability is only about, believe it or not, 100 years old. Probability is as old as human beings. People have often wondered about chance and all that. But the putting of probability in a rigorous framework is really new. It's about 100 years old, which is something quite interesting because I've said this in a bunch of classes. You may have heard me say this, but I'll probably be repeating myself to some of you. When you come to college, usually your first year is spent learning things that are at least about 1,000 years old. Your second year is spent learning things that are maybe 500 years old. And by the time you come to your later years, you learn things that are about 100 years old, things like that. So you're at that stage now. So you're learning probability theory from a very rigorous point of using sets and precise, real analysis, dare I say, concepts, which is new, because people like Newton, for example, Isaac Newton, they were very intrigued by probability, and they would write letters to each other and challenge them. Like Isaac Newton would challenge his mathematicians. Like, I have this gambling game, and I want to know what are the chances of it. Do you know sometimes they got the answer wrong? They did because they didn't really have the rigorous tools that we have today. I always tell students, can you imagine 400 years ago, people would write letters asking math questions. Now, do people communicate nonsense on Twitter and all the rubbish? So how degraded communication has become. It used to be a thing of such high value that people would challenge each other. Not saying that people didn't have egos, right? That's as old as human beings. But the things people talked about, it was expensive to send a letter. Now it costs nothing, or we think it costs nothing to use social media. I think the cost of social media is coming up, right? Maybe not in dollars and cents, but anyway, so okay, so this is a simple example. Let's do one more. And this will actually lead us to the thing I want you to work on together as a group. But we'll look at an example first. So a camp of students has, well, there's 110 of them. Now, this can be quite confusing. So let's parse through the information. So one thing about probability is you need to understand that when we say something like this, don't have tacit don't make tacit assumptions about things that you are not told. So if I say 75 speak English, I think in day-to-day speak, we are less precise. Somehow, when we say things like 75 speak English, we tend to think that they speak only English. We add these things which are not going to help us in a rigorous study of probability. So don't do that. This is a little bit difficult because the language that we speak is less precise. I'll give you a very simple example. You go to a restaurant and they're having a promotion. So they'll say, choose for your entree, you want a salad or you want breadsticks or something like that. Okay. Everyone knows that you're supposed to pick only one, but do you know in math, all could be, I could do both. Someone's going to look at you very strangely and say, I want both. No, you're supposed to. What you mean is, I want salad XOR breadsticks. You should actually say XOR. If you mean choose one and only one, you should say XOR. No one talks like that. So what I'm saying is, our ordinary speech is less precise. In math, all could mean both. So here, if I say 75 people speak English, it doesn't mean they speak only English. See? So don't make these kinds of assumptions that we tend to make when we speak, because we're just less precise. Language is not as precise as math, all right? So we're, okay, so again, you see, if I tell you 30 speak English and French, they could possibly speak something else as well. We're not discounting that, you see. So how do you solve problems like this? Okay, how do you find how many students speak this, you see, but not French and things like that? So the solution to this kind of problem is you build a Venn diagram. Now, I know some of you who are have a mathematical bent are probably screaming inside and say, hey, these aren't sets, because sets have elements, but these are numbers. Okay, so I am doing something sloppy here. This is not a set containing the number 20. There are 20 people here. So, but I hope you'll pardon me this misrepresentation. This is not actually how you write a set, right? Because a set is a collection of elements. There are 20 elements here. To save time, I didn't want to write person 1, person 2, person 3, person 4, up to person 20. But you know what I'm trying to say. So this is a simple, it's kind of like when you learn how to multiply in school before you had calculators and all that. You know all those tricks, you just put a zero here, move the thing by one space. And what are you doing? You're actually doing bulk operations, which is actually multiplying by 10, but you didn't want to teach students at that time and things like that. So that's actually what's going on. This is a simplification of, it's trying to make it a little bit faster, basically. Okay, so I think you can understand this picture, right? Let's see where this information comes from. Why is there a 20 there? Well, we are told that, wait, so hold on. Wait, why did I feel a 20 there? Hold on. Oh, no, no. I've already started to break it. Okay, so we are told that 30, okay, 33 speak English and Spanish. Okay. 33 speak English and Spanish. So the only way that, so we know there must be 33 people in this section. See? Now the discovery that this is 13 comes later. Right? So I don't want to belabor this point, but I think this is quite intuitive. If you know how to read the thing, you will know the order in which these numbers get filled in. So let's see. Okay, so I think, let's see, the information that they tell us, see, yes, okay, so the key is 13 speak all three. So the first number that gets filled in is 13. See, there are 13 people here, which means there must be 20 here because we're given the information about the 33. And I think you get the idea. So once you've filled in this one, this is like playing Sudoku a little bit, simple one. So then you can fill in these, and then these are not known yet. So you do a little bit more math and arithmetic and multiplication. So, so let's answer some questions. So English and Spanish, but not French, which means English and Spanish, but not French. Oh, which means, oh, yeah, so that's right, like that. So that was actually guiding you to filling in the slots like that. Okay, so you get the idea. So here are the answers. I don't think I need to really teach you this one. You start off with anything that you fully know, then you start filling in the things that you can use after you have set in the number that you're 12 you know. Right, bearing in mind that these are not elements, they are the size of the set in that region. All right, and so on. Okay, so I think there's nothing really of much. I don't think there's anything. Yeah, I don't think there's anything that I need to say. It's just a lot of arithmetic, really. All right. Okay, so I have some paper here. I'll give a sheet to every table. I want you to create a question with, I don't know, different. You can use the same context if you want. You can dream up another context, but limit it to 3 sets. Don't. But 3 sets that intersect in the most general way, like what I've done, and put some of your own numbers in and see if you can fill it in correctly. Every region should have the number of people in there. All right, you can reuse my example. Let's use this example. Just show me that you know. And you know what would be good? Show me the order in which you fill in the stuff, right? How do I know this is confirmed first? And then how do I fill in the next one? So you can You can use the same example as mine, but put different numbers, all right? Do you know that now you are playing the role of the professor? Do you know that these kinds of questions are not the easiest thing to write? You know why? If you simply give numbers, right, it may fail, you know. You may find that your math doesn't work and you have negative numbers, something to compensate for it. So that's why I wanted to do that. I wanted to think, how would this work, right? So actually the cheating way to do this is do it in reverse, which is start off with a complete picture, but that's okay, don't do it that way. Okay. But try. See if the numbers that you just pick off and does it work or not. Sometimes it doesn't, so you might need to modify it. Yeah. So that was the merge. Oh, does it? And notice, is there a possibility that people speak none of them? Yes. You see? Now, in your case, it might turn out to be zero, but if it turns out to be a negative number, then you need to tweak your.
Okay, so we know 4. And then that. English. No, you're so good. Or speaking. The one that's aged. And then.
And then we're going to oh, you did that?
Like I thought I said that, but I accidentally saved as a draft. So I said that like at 1:45. But I was at doctor's.
Oh, okay. Yeah. Yeah, that's right.
Okay. And then span is 30. 13. And then we'll add all of that up. So, and that's that. And then 8, that's 30. So 25 adults.
We should go.
Yeah, I think.
Okay, so just, if you check it out, good, right?
We have a lot of people who cannot see.
That's fine. As long as it adds up, then it's okay.
I'm not good. That's
That was kind of fun.
You gotta make a very flat.
Okay, so it's not that hard, okay? And your numbers can be very skewed, or it doesn't matter. It's just an exercise in being very careful in defining things. Right? Who speaks what and what doesn't mean they don't speak something else. And you might have some people outside, okay? And I don't mind if you want to hand it to me like after class or what, you can always leave it in the you know, my office has these I don't know what you call it, trays, right? You can always pop it in there later. If you feel like, oh, I want to work more on this, that's, as I said, there's plenty of these in-class things, and it's more to help you learn, not whether you can finish it on time or something like that. Okay, good. So let's move on with our slides. Now, I don't know why, please forgive me. I don't know why I suddenly used you here. I'm kicking myself for that, please, okay? I almost always say S, so I don't know why here I use you. And it's probably in your slides as well. So, I mean, there's no harm. You can leave it as a U, but typically we say S. I don't know why I use you here. I have no idea. But normally, the universal set in probability theory is called S. I guess some people say U because it's universal, but okay. So there are a few things which I think will not come as any surprise because intuitively we understand what these things are. If you are a set in, if you are a subset of the universe, then the complement of U is, well, A prime. Some people write this as A superscript C. It's up to you. In my line of work, I write set a lot. I write sets a lot, so I don't want to waste time. So I just put a prime like that. So A complement is typically written as A prime. And the definition of A complement is everything that's not in A. Okay? Everything outside A. In the universe, of course, but not in A. All right. Now, this is not very important, but we will talk about another way to denote this. What is B minus A instead? Okay, how do you take? Okay, so this is where it's not that computer science understanding of subtracting elements of one set from another. It doesn't mean that. All right, B less A just means everything that's in B that's not basically. All right, everything that's in B. Now, again, in set theory, O and N are very, very important to distinguish. And means both have to be true always. All right. So you are in B and you're not in A. So here's an example. All right. Mm. So can you give this a try? So A is the set of 1, 2, 3. B is, well, the collection of 1, 2, and then A. So what's A minus B? So the definition of A minus B for sets is everything that's in B uniquely in B, not in A at all. Right? So I think this is not a very difficult question, is it? Right? What's in B that's not in A clearly is just this set. This set, this thing, this entity is not a part of A at all, right? And it is in B. So this actually is the only thing that A minus B has. So oh, sorry, was I saying B minus A? Okay, yeah. So we have to be very careful. A minus B means A minus B by definition is
everything. A minus B is, yeah, A minus B is everything that's in A that's not in B. All right. So everything that's in A that's not in B. And so A has the elements 1 and 2. These are not found in B. So the answer for this is it's not just listing down the elements. It is the set of elements that are unique to A, basically, right? Okay, so let's move on to something else. So the union of two sets, A union B, is, see, now there's an OR expression. Again, this is not proving anything, but it's a simple visualization of what's going on. A union B is the collection of everything that's either in A or in B or both, right? Again, so in math, saying or is a broad statement. It could mean and. All includes the and case, right? Of course, we don't talk like that, right? In ordinary speech, when we say choose A or B, we don't allow you to choose both, but math does include that case, all right? Okay, here is an example. Example 10. See? So what's A union B? Well, combine the two. Just make sure not to repeat anything. Because we know that the set's elements are unique. We do not write one twice. All right. So the answer for A union B here is 1, 2, 5, 7, 9. The set containing 1, 2, 5, 7, 9. And just to reiterate, it's not 1, 1, 2, 5, 7. You don't repeat the 1 and, as I said, you can't exhaust elements in a set. It's not that you've taken out one physical entity and then it's gone now. It's there, right? It's a membership list actually. It's not a list of actual tangible things, right? That that you can take out. Okay, so yeah, okay. So let's go on. Now we can extend the definition of union to when you have a countable sequence of set. Okay, what do I mean by countable? So, of course, those of you who have done real analysis will know what this is, but don't worry if not, I'll explain. Countable just means can be put in correspondence with natural numbers. So to use lay people speak, it just means you can write it as a 1, 2. You can list it down in correspondence with 1, 2, and 3, right? So the set of real numbers is not countable because you cannot, for example, you can't say what comes after 1 in whole numbers 2, but there's no meaning to the statement what comes after 1 in real numbers, which is why it makes me cringe when I was watching a sitcom the other day and someone was saying, what comes after 18? And, and he said, of course, it's 19. Yeah, if you're talking about integers, right? In real numbers, there is no answer to the question. You cannot list the next thing that comes. So if that's a simple illustration of why we say the real numbers are uncountable or not countable. So a countable sequence of sets means you can list down the index in correspondence with the natural numbers 1, 2, 3. So what's the definition of this? Again, I don't know whether you need to have a healthy respect for the infinity symbol, right? It's not a number, right? It's a symbol, right? This means it is the collection of all things that belong to AI for some I. No one likes this. Everyone thinks this is much more cool, but actually this is more enlightening to this. This means nothing. This is a symbol. This means the collection of everything that belongs to some AI. All right. So, so let's look at an example. All right. So let's define the countable sequence of sets AI to be the set containing the element 2I. Describe this in words. Anyone? Anyone want to try? What is the union? The countable union? Yes.
All even.
Yeah. So all even positive. Yeah. Okay. I did. Yeah. So I do say that it's all the natural numbers. So it's all positive even numbers. Good. Good. Right. Something like that. Good. All right. So, I can't stress this enough. There's no meaning to say A infinity. Because you cannot put I equals infinity. This is a symbol. It just means you are a member of one AI. Which one? You have to be a member of at least one of the AIs. All right. That's what this set collects. Okay. What happened to? Why is this word partially blue and partially? So weird. Okay. Never mind. Okay, let's move on. Okay, the intersection of two sets is written as A intersection B and is defined as it contains all elements that belong to both sets at the same time. Okay? And of course, you can draw a picture if you want, if it helps you. And we can extend this definition of intersection or a finite intersection. This is called a finite intersection because there's a finite number of sets that are intersecting. You can do this as a countable intersection as well. This means the set of all elements that belong to all the AIs. All right? Okay. And I think we'll just slot this in. If two sets have an empty intersection, the word we use is they are disjoint sets. That's just a definition of the term, right, that we use. Okay, let's look at some examples. So if I define A1 to be the set with, well, just one, and then A2 to be the set with 1 and 2, and you get the idea, then what is this? Right? Can you do this quite quickly? What is the intersection, the countable intersection of A1, A2, and so on? Which element belongs to everybody? Right? Yes. Yeah, just a set continuum. That's it. Only one is like that, right? No one else. All right. Good. All right. So it's just a set of one. Again, don't do it this way. In other words, don't say, well, if I intersect 1 and 1, 2, I get a 1. If I intersect 1 and 1, 2 and 1, 2, 3, I get a 1. And that kind of thinking is still trying to take an infinite thing and put it in the finite. Most of the time, it's okay to do that, but it can lead you to wrong conclusions when it can break down that kind of argument. So don't do it. I'm most fearful that people think this is a continuous process. So let's take A1. Let's intersect A2. Let's intersect A3. Let's intersect A4. Then dot, dot, dot. Yeah, what does dot, dot, dot mean? What are you doing? So I'm trying to rid your mind of these kinds of what's the word for it? The non-rigorous thought. Right? I think there are people who think this is an exhaustive search, you know. Let's do A1, intersect A2, intersect A3, intersect A4, dot, dot, dot. What's dot, dot, dot? What does it even mean? You can't finish doing the intersection, and that's why the definition is very important. Don't do that. You're not supposed to do that. The definition of this is not A1 intersect A2, intersect A3, dot, dot, dot. You can't. Everything in math is hard, okay? I'm not denying, okay? But actually, it's made more difficult because we are not precise in how we think about things. We do things which no one told us to do yet. And that's why I'm harping on this so long. What's the definition means? Which element belongs to every AI? And if you think of it that way, you can get the answer. And without resorting to these strange mental exercises, yeah, what are you doing? You can't finish doing it. And that's the point. You're not supposed to be doing that. Look at the definition. All right. Okay. So we have that. So for each positive integer n, we define an as, okay, this is not a difficult problem either. So a1 is a set with 1, a2 is a set with just 2. So what is the countable intersection of all these sets? Does anyone belong to every single one of them? Right? They have nothing in common, so it's empty. Right? Right? Nothing belongs to everyone, so it's empty. Again, don't do it as Well, if I intersect 1 and 2, that's empty. If I intersect 1 and 2 and 3, that's empty. You know what you're doing? You're doing an induction. Do you know induction only works for finite things? You're not supposed to do induction to prove infinite things. All right. So definition, very important. Okay, I think let's see. I'm supposed to go on to 14. Okay, so one more. Express each of the following events in terms of A, B, and C and some kind of operation. Okay, this one I want you to work on with me. This is a good one. So what do we mean using set switch, if you like? At least one of A, B, or C occurs. This is not so difficult. Anyone want to try? How do you use just the letter? Okay, this is almost like a game show. Using just the letters A, B, C and the symbols union and intersection and prime, how would you express at least one of A, B, or C occurs? Anyone? Yes, it would. This is A, U, B, U, C. You get it? Because what does that mean? It means you belong to either of them, two of them, or any other, but at least one of them. So that's exactly right. Okay, so you know where this is going. Some of these are a little bit more challenging, and my advice to you is if you're trying to answer these things, draw a picture, draw a Venn diagram with the most general step. The most general way you can draw three sets is to make you do that thing that you did, that English, French, Spanish exercise thing, and shape places in that will help you, right? So give it a think. At most, one of A or B or C occurs. So how does that work? Right? Give it a think, right? Before I show you the we will certainly discuss this, but I want you to think about it with your group first of all, right? What do you think is the set representation of things? And bear in mind, some of them are quite complicated. It's not everything has a simple, short solution. Sometimes it's quite long. The expression need to be quite long. Draw a picture, right? Let me help you out with B. If I say at most one of A, B, or C, can you give me one uh, sequence, if you like, that is acceptable? What do I mean by at most one of A or B or C? Yes,
A and not B.
that's right. A did happen, and B and C both did not happen. But that's just one thing. See, so are there other ways to fulfill this? Yeah, okay, there are. So I think you're on the right track. So as I said, some of these expressions may be quite long, but try to write that all and see. And please discuss with your friends. Okay, that's fine. I actually prefer you to discuss with them and see if you can come up with these things before we talk about it together. Okay. Let's see if you agree. So of course, we have talked about this one. The first one is A union B union C. And as I said, B is not the easiest to express. So here's what I have. Now, there could be equivalent ones, and you could show, we'll teach you some relationships that actually can show the equivalence of what you probably said. To me, this is what makes sense to me. So this is, see, A happened, and B and C both did not happen. And then, of course, you have to swap the roles. It could also be that uh, B happened, but A and C did not. If the C happened, and then oh yeah, and then I said at most one happens, so it could be none happen. So nothing happens. A and B and C all do not happen. That's basically it. Now, why are these connected with an or? Because you can't have this and this happening simultaneously. Because here you're saying B did happen, here you're saying B happened. So you have to connect them with an or. All these qualify to say at most one of them happened. At most one happened means it could be none of them happened. And so we have this expression. Is this okay? This is one of the slightly more technical ones. Right? Think about it, all right? Okay, then let's go on. C was, what did C say? C says, no, oh, none happens. Okay, so none happens. This one, I don't know how your mind works. How many of you actually wrote this as your answer? Like, or how many of you went with this job? I'm just interested. Okay, so more hands are raised for this one. I think this is how most people tend to think. I think I'm like this as well. Some people, interestingly, this comes more naturally. But I think it's a bit rarer to be this kind of person. Both are correct. And you will learn with me that these two are actually equivalent. They're the same thing. Right? In other words, I'm going to teach you how to do an associative law thing for sets. And you break up a parentheses by taking these terms in and swapping the rules. You can learn a bit operationally like that, but you can also think of it using arguments if you like. This is A didn't happen, and B didn't happen, and C didn't happen, which is a very natural way of thinking about it. But think about it, isn't this the same thing as saying, this is, well, at least one of them happened. So when you say that this is not what I want, it means none of them happened, right? Now, you need to be comfortable with both forms. Even if one is not natural, you need both because, let me tell you why. In solving probability questions, it is often much easier to ask you to compute this probability that you do. This is usually a nasty mistake, not the nicest thing. Although they're equivalent, you need to realize that this and this are the same because it will help you get the answer to this probability of that event. All right. So you need to be comfortable, even if one doesn't come as naturally, you need to realize that they're the same. Okay. Let's look at another one. D says oh, this is easy. All three occur, of course, okay, so of course there's A intersection B intersection C. Exactly one. Did y'all get this one? Exactly one of A. This is not that hard. Exactly one occurs. So this would be something quite similar to B, but less complicated. See, this is A happened, but B and C did not. That fulfills that. But we didn't say which one. So you need to cycle through all the possibilities. This is A happened, but not B and not C. This is B happened, but not A and not C. C happened and not A and not C. And why do we separate them with an or? Because all of them qualify. Any of them would. And anyway, you can't have these things happening simultaneously. There's no problem. The probability of that happening is zero. You can't have B not happen and happen. So so are you all bothered by connecting them with it? No, right? Because all of them fit the criterion, and all is broad. Anything that fits the criterion gets dumped into the all like that. All right. Okay, let's see F. I'll come back to that. F is events A and B. Oh, this is easy. A and B happen, but not C. So A intersect B intersect C prime, right? Like that. Now, Either A occurs, or if not, then B also doesn't. Okay, this one's quite strange. Let's work that one out. Do you agree with G? Either A happens, or if not, then neither A nor B happens, or something like that. So, right, this is A happens, and this is, well, neither happens. So, that's how you. All right. I think drawing pictures is easy. Intersections are easiest visualized. If you do a cross hatch, like one of them you go in this direction, one go in another, the place where you get crosses. Again, Venn diagrams are not a way to prove things, but they are a very useful way to visualize things. Okay, so something like this. So you can go back and draw these out if you want. Yeah, these are not the most beautiful things, but you get the idea. You know, it's not the easiest thing, and I'm not going to ask this for exam, so don't worry. It's not the easiest thing to look at the picture and derive uh, the set operations that led to the picture, especially if the picture is quite complicated. I think sometimes using words is actually easier than getting what sequence of sets led to this picture. It's not the easiest thing to do, not for me anyway, right? But yes, so usually we don't work in that direction. Usually you draw this after you have a complicated expression and you're trying to see what it is that you're doing. So I will not ask you, okay, look at this picture and work backwards and get me the expression. I mean, what's the point of that? No one works that way, right? So these are meant to help. It's not meant to torture you or to be something that doesn't make sense. Okay, so let's move on. I think there's a little bit more that I want to say. Yes, okay, so some properties about sets. So we'll get into that and finish with one example for today. So this is what I just promised you. You can do some simple operations on sets, and they're pretty intuitive. All of these can be proven. And I'll tell you, if you wanted to prove them, how would you prove them? They're quite tedious to prove. You'd have to show that this expression is a subset of this and vice versa. So it's not, and sometimes the proofs a little bit are like just using arguments and logic and all that. So we won't go into a rigorous proof of these. We just assume these to be known. So, but they can be proven, all right? So how do you break up the parentheses with an intersection sign? Well, you do quite, it's the parallel, I would say the analog with arithmetic is this is like multiply, and this is like plus. All right, so it kind of works that way. So that's how you open up a parentheses with sets, and you can do that for number 2 as well. See, this is the thing we just talked about. If you say none of A or B happened, you're saying this. You're saying this. So this is called De Morgan law. You might see this, the name of the person, but so just remember it as the complement goes in the swap side. Okay? And the sad part about this is this kind of notation tends to lead students to think that this is like a number. Oh, it's not. And the proof of it is not based off an induction type proof. This is proved separately, but it is true that it extends to countable unions or intersections. So, right? Swap signs, complement moves in. Right? Here's another one. The size of the union of two sets, if it's finite, right? If both are finite, is this. All right. Again, the proof of this it's not the most simple thing to do. You of course you can draw a picture and convince yourself that this makes sense, but that's not a formal proof, right? If you draw two sets and then there are people here, there are people there, and I've counted when I do this plus this, I'm counting the intersection twice, so I take one away. Yeah, that's an argument that you can use to make it make sense to you, but it's not rigorous at all. You cannot use a picture to prove things like that. But it's a useful visualization. Here's something that you need to know. If A is a subset of B, and this is true even if B is an infinite set, all right? Then the size of this set will always never exceed the size of the other. Right? Seems intuitive, and it is. Okay, but it's something that we want to do. So we will end today with just example 15. And what is, oh, okay. Why am I asking you to do this? Oh, okay. I want you to okay. I want you to actually solve this problem. So 35 candidates. Okay, again, there's this thing. Okay, don't assume anything. If I say this number speak a certain language, it doesn't mean they don't speak something else unless I say so. So try to solve this using either a Venn diagram or using some of these properties that I've just that I've just introduced here to help you. These are universally true, uh, but you pick the way that you like. If you like a Venn diagram, go ahead. Right? You can. Right? It's not a very difficult problem. This, right? Right? Because here, this is actually slightly simpler because there's only two languages that are being considered. So the universe is smaller here. So see if you can work this out. You can draw a picture. You can use a Venn diagram if you like. Uh, And I think you need to complement that with some of these properties that you've learned. Do it both ways. Use formulas if you like, and also use a Venn diagram to convince yourself that you know the answer to the problem. Right? Maybe since we have some time, we might be able to move on to maybe example 16. We see how this goes, right? Shouldn't take you that long, this one. If you've done the English, Spanish one, that one was more complicated. Okay, so are you getting, okay, you don't have to write all these things down, okay? But I'm using formulas, if you like. Right? So, as I said, you can do it this way, or you can draw a picture. See, how did I know that this is 33? Anyone want to tell me? How do I know this is 34? Yes.
To abstract a number that's speaking neither.
That's right. Because we are told to speak neither. There are 35 people in this universe. You know to speak neither, so they don't qualify to be as union A. So if we know NFUA must be 33, because the other 33 people speak at least one or two. So that this is being very precise in how you count, and who fits what criteria. Like that. Again, if this kind of thing is not so suitable for the way you process this kind of information, you can draw a Venn diagram. I'm just demonstrating the use of this thing that I just did. The size of the union of sets is the sum of the sizes of individual subtract one of the intersection sizes, right? And just subtract once. Okay. I think we do have time, so let's move on and see. Okay, there's a bunch of examples we're going to look at. Okay, let's look at example 16. Yeah, I think we will end with this one. Can you convince yourself that A and B are any two sets? And when we say any, you have to draw them in the most general way possible. Basically, that use Venn diagrams to prove these things. So I'm not asking you to prove it rigorously, but convince yourself that this expression leads you to B. This is very, very important because you will see this in probability theory. And I'll start talking about this actually. I like to have students visualize this as, let's say you are B and you have a friend called A. So B is the event that you go to eat at Phelps or something. Now you either go eat at Phelps with A or you don't. Isn't that a truism? Isn't it true? You sometimes you go with A, but other times you don't go with A. Now, I'm not saying you didn't go with someone else, but as far as A is concerned, you either went with A or you didn't. See? So this is the event that you go to flight. But I either go with A or go with not A, someone else. So see, it's all. So this is I go with A, so it's N. This is I go without A. And if you draw a picture, it's going to be very, very clear, right? Draw A and B, draw this region, and combine the two, you get back. Okay, this one may not be so intuitive, right? Looks kind of weird actually, but can you convince yourself that this makes sense, right? Because A or B, this doesn't even change. Isn't this true, right? Because AC intersect. Okay, you might think, what is the purpose of the professor writing things like that? Can anyone think? I want you to think about my question, not proving whether this is true. I think most of you can convince yourself that these things make sense, especially if you draw a picture. Why would I ever want to write things in this strange way? I just realized why would sometimes when I generate these examples, like the gift that keeps on giving, like it's like sometimes I didn't even realize why I picked it. I just realized why is this form useful? Can anyone tell me why? Why would you do that? Isn't it easier? Only a moron would write this thing. Well, no, not just morons would do that. What is the purpose of this more complicated expression that looks to be like making things worse? Why is this? Or when would this be? I would be quite happy if someone can think of what I'm trying to say. They're equivalent, they're the same thing. Why would this be a useful thing? And in what context would this be a good thing? Sorry, go ahead.
People cancel out for.
Okay, so I think you're getting it wrong. It's not so much of a canceling term, but it's something to do with mathematical convenience. What am I getting at? What is nice about this? I know this looks awful compared to this. This is simpler. But what advantage does this have? And I wish my probability professors told me things like this. They led me off to learn things on my own. I'm trying to short circuit it for you a little bit. What is the advantage this form has over? Yeah.
Maybe you know something about A naught and B, but you don't know.
Yeah, so getting warm, but it's a little bit more basic than that. It's something to do with sex. Something to do with sex. And this really should blow your mind a little bit. I'm hoping to blow your mind in the last few minutes of class. Right? There's something very nice about writing this way. What is it? Wow, I'm never going to forget this example anymore. Because I had to use this when proving probability stuff. See? What's nice about the relationship between this and this? Right? Anything jump off at you at all? Yes.
Like you know that B pulls A naught
No, we don't know. Right? B and A have a very general relationship, so they are not equal. Or they could be, but we cannot see that. There's something about this and this that's very appealing and helps simplify a lot of things in probability. It's not very fair of me to expect you to know this now, but if you did, that would be great. There's some feature that these two components have that's very nice. Yes.
They're mutually exclusive.
Oh, yes. And what's the word we've learned today? They are disjoint. You will learn that in probability, if you can establish that two sets are disjoint, it helps a lot. You know why they don't intersect? They are mutually exclusive. And when things don't happen together, it simplifies a lot of things. So you see, a seemingly complicated thing can be useful. Do you agree that that is joint? How do I know that it's joint? Well, this has an A, this is an AC. how can they not be disjoint? They can't. In fact, do you realize that if I take any set and intersect something, it only gets smaller potentially. It never gets bigger. So even if I just looked at this, they are already disjoint. Making a set intersect something else is not going to make it less disjoint. That doesn't even mean anything, right? It still stays disjoint. And now you have equivalently written this, which are potentially not disjoint. It's a union of disjoint sets. So you know what some people will phrase that? Can you express A union B as the union of disjoint sets? That would have been a more challenging thing to do. And I have sort of given it to you and we discussed it. So don't forget this. It is sometimes very useful to be able to re-express two sets that are union that are not disjoint as a union of two disjoint sets because it helps a lot. Some people have a notation for when they are not a verb, I'm going to make it a verb, when they're unioning, right? When they're combining disjoint sets, you know what they do? They put a little dot on top, you dot, like that. It's like to tell you, hey, you are taking the union of disjoint sets. And that's special thing. Because nice things happen when you take a union of disjoint sets. I mean, I don't do that because I don't think it warrants introducing another symbol. Math is very symbol heavy and I don't like unnecessarily giving more, but you might see this in books. When you see a union with a dot, it's a union. And a lot of special nice things happen. Okay, good. I've enjoyed today's talk. I hope you have. And I will try to open up a homework where you cannot do all the problems yet. I think you can do one and two or something. Let me check. Right? So I'll open it. I'll send you a video. I don't spring surprises and sneak in a homework and not tell you. I always tell you when I give a homework. Okay. So I'll see you all on Thursday. Right? We'll continue then. Oh yes, before I forget, if ever you have any questions, please come to office hours. I will help you. If you see the door closed, and you most likely will, because if you know my office, you might not. I'm at an intersection, and very noisy. Okay, so it's a lot of speech and walking and all that. So knock on the door, please, and please come in. All right, and I'll let you in, of course. But if you have knocked the door, because I don't know your house, I don't have X-ray vision. Okay, so knock on the door, and I'll let you in. Okay.